going to hear from John in just a minute, but John has been the chair of Geological and Mining Engineering and Sciences up to about a year ago. And so that's how I got to know John pretty well as part of the leadership team of the college, which has been terrific. So we are live streaming on Facebook. Hello, everybody out there on Facebook. And I am going to make sure I can find my slides. Very excited. This is the second of 11 Husky Bites this fall. This year we're going to wrap it up the week of Thanksgiving and not spread into December, because we figure people are going to be back to all their parties and things and aren't going to want to kind of go to a Husky Bites, or they'll be too busy, or they'll be at parties, you know, and that sort of thing. So I'm going to make sure I can share screen, which I think I can, and then go to present slide mode. All right, can you see slides? Yes. Excellent. All right, well, I'm a little early on my introduction, but I'm eager to get started. So let me just begin by welcoming everybody to Husky Bites, which is a live Zoom webinar where you can ask questions, or you can watch it live on Facebook live stream. It's an educational free webinar provided by the College of Engineering at Michigan Tech. I am the host. My name is Janet Callahan. I am Dean of the College of Engineering. And this evening's Husky Bites is sponsored by the Department of Geological and Mining, Engineering and Sciences, which we've just discussed has 4 different undergraduate majors and of course, appropriate graduate degrees in the field. So thank you for joining us. And if it's your first time joining us, an extra huge welcome. We did send something like 46,000 postcards. So I wanted to make sure people knew about this, because this is now our 4th season. And I had been meeting alumni who hadn't heard about Husky Bites, and I wanted to make sure everybody knew about it. So this is our fall lineup, or our quote unquote menu. If you missed the first one, you can watch it. They are recorded and they are posted on the Husky Bites website, which is mtu.edu/huskybites. And so we're on week number 2, and I'll talk about the rest of, well, here's the rest of the season right in front of you. You can see it spans a whole bunch of different fields, disciplines, and areas of interest. As I mentioned before, we are live streaming, and I'm hoping to queue up a poll. And so if you've never taken a poll before, down at the bottom of your Zoom tab, there should be a place where you can fill out a poll. And there I see the poll has been launched. And so who's joining us today? And this will help us know who our audience is. And so there might be any one of these things. And sometimes there are people from 3 or 4 categories. And so if you're from 3 or 4 categories, I don't know what to say, pick the majority category. So we've got already, golly, it looks like I don't know, can you see the poll right now, John?
Yep.
So you can see it coming in live?
Oh, yeah.
Excellent. So just to kind of speak this out loud, we've got 76% of the people joining us alumni. We've got 4 students, which is 5%. We've got 4 family, who are our family of a current or future student, friends of Michigan Tech, about 4. And so we're, I think you've pulled in a lot of alumni, John, this evening. So that'll be fun. Well, and okay, we can go ahead and stop that poll. Thank you again, everyone, for joining us. Welcome to Husky Bites. All right, so I want to go to the next slide. If you are an educator, welcome. I do want you to know that you can get professional development credits, which are called sketches here in Michigan. And if you are not in Michigan, we have had other teachers arrange to get professional development credits by talking with their regional coordinator. So if you have any questions about this, just drop us an email to engineering@mtu.edu. So I do want to give a shout out to next week's topic, because I think it'll be a topic of huge interest to people. We're going to be featuring Lift Bridge, which is a Michigan landmark, and our own professor of civil and environmental and geospatial engineering, Teresa Alborn will be the featured speaker with co-hosts, two of our former students who are alumni now, Michael Prost and Emma Beachy. And so join us for that. If you join us early, you get a weather update, and welcome again. All right, it is my pleasure at this point to introduce my co-host. And the function of a co-host is to help us with difficult questions, to help me in case my internet connection goes down, and to just kind of, make fun of our speaker. No, I didn't mean that. I mean, to have fun with our speaker. So our co-host is Professor Eric Seagren, who is a professor of civil, environmental, and geospatial engineering, which is actually a new name for the department, reflecting the fact that it now offers geospatial engineering. And so Eric joined our university in 2010. Before that, he was a faculty member at a different university. He is a professional engineer, and his field is environmental engineering, and his particular research interest is I would say in situ or sustainable ways to clean up environmental pollution, or to be a little more technical, environmental biotechnology, in situ bioremediation of contaminated subsurface contaminants, innovation of use of waste materials, and more. And so in the picture, you can see a picture of a 53 Chevy pickup in good running order, and it's blueberry colored. And we're pointing that out because Eric has challenged John, who, in addition to being a faculty member for the Department of GMES, John is also a blueberry farmer. So they're what they joke about with each other is that they're going to fill up the back of the pickup with blueberries one day for a parade, and probably win the parade. And I don't know if you definitely made, 12,000 pounds would certainly fill that pickup, I would say, right, John?
Oh, yeah, we've filled that pickup a couple times this year, in the first week.
Well, and so Eric, I'm going to stop sharing slides. I believe that was my last one. Yep, see, that's my reminder. And so people can see your face and John's face. And would you go ahead and please introduce John Gierke, our featured speaker this evening?
Certainly. Thank you for that introduction, Dean Callahan. And it's my great pleasure to introduce my colleague and friend, John Gierke. I think John and I have known each other professionally, perhaps on the order of 20 plus years, which suggests we're not really spring chickens anymore. But we've been colleagues here at Michigan Tech since I moved here in 2010, as Dean Callahan said. And although he, I think, likes to tease me terribly, John is quite an interesting individual and a good person to be able to call your good friend, I think. And I tell just a small anecdote about that. Many years ago, my daughter was having appendicitis, and my wife, Jennifer Becker, was out for dinner with John and a faculty candidate, and I couldn't get a hold of Jennifer. And so I called John, and within a couple minutes, John had Jennifer on the way to the hospital and had a home lined up for me to drop my young son off so I could go to the hospital with our daughter. And so that's just the kind of guy. He is there in solving problems for folks. And I think that's what makes really John a special person to know. Some of you might know John grew up in Sault Ste. Marie, and that's where he really developed his love for the great outdoors. And those of you who know him know that he does love the great outdoors. He loves to fish and developed a love for hunting there in the U.S. Eastern UP, and spent 2 years there at Lake Superior State University before he transferred to Michigan Tech, which used to be a fairly common pathway, I believe. With his love of water that he developed there in the Sioux, he went into civil engineering with an emphasis on environmental engineering. And that led in his graduate and faculty career into interest in the groundwater and subsurface water and its movement and remediation. And of course, that's the kind of topics he's going to be talking to us about today. I would just add to what was said earlier. It was mentioned about his blueberry farm, and he and his wife, Lynn. I think Lynn should be mentioned because I think we all know who really does the hard work at the farm. But Lynn and John have a wonderful blueberry farm in Chassel, and if you haven't been there, I encourage you to visit it next August. And maybe we'll be driving around with a blueberry pickup truck. Who knows? So tonight, John's going to be telling us about drilling wells in the Keweenaw, needles in a geological haystack. This sounds fascinating, and I look forward to hearing what John has to say.
Well, thanks, Eric. I was just thinking, I think the first time we met was at a Association of Environmental Engineering Professors conference in Maine, and that would have been 96 or 97.
Probably, yeah, yeah,
And my kids were really small then.
yeah.
Sure.
And I, yep, that's right.
All right. Well, we'll just get this on the road. I'm going to talk about water wells here in the Keweenaw Peninsula, and the complexity or challenge of siting wells that are used to provide community level water quantities in this beautiful and unique geology that we have here in the Western UP. First of all, I'd like to mention, even though I say the word geology a lot, and I'll say some rock types, I'm not a geologist. As you heard, I'm a civil environmental engineer by training. I work with water that is underground, and that's why I'm in the geological engineering department. So I study the spaces in rocks and in unconsolidated materials. And I apply that expertise to groundwater availability and like Eric, on cleanup of contaminated groundwater. I have a couple of pictures here of some field work I've done. This is the lower one is some pumping tests we conducted in wells equipped with rope pumps in Nicaragua. And so this test, we're pumping water at about 5 gallons per minute, filling up a 5-gallon bucket in about 1 minute. And then the picture in the upper right is a student project at the Keweenaw Bay Indian Community Fish Hatchery. I'm going to show you more about that. That's a pumping test in well 5. Students of mine have been working on wells there from starting well number 2 up through well 5, and we've now sited a well 6 to expand the hatchery operations. And I want to point out the water that you see spewing out of that pipe is about 150 gallons per minute. And so we use that barrel to calculate or to measure the flow. We time how long it would take to fill it, but we didn't anticipate the force of that water. And so it was a pretty big challenge to do with water spraying all over. So all of us have seen water wells of various kinds. The most common are pictured here in the middle and at left. And those are the well heads, and they're actually just the top 1% or less of a well. The picture in the middle is a irrigation well at my farm, and so you see some electrical conduit where the wiring goes down to the pump. The pump hangs from that galvanized fitting here in the center. This well over here is an 8-inch production well at the Keweenaw Bay Indian Community, and these are some of my students, and we're working on a water project about 4 years ago there, trying to figure out what was causing the plugging of this well, and I'm going to show you some more information about that. So it's 8-inch diameter, and when it was initially installed, it could produce water at about 400 gallons per minute. Now it's a little less than a third of that because of this plugging issue. What's shown over here is the pump that is normally in this well, and the piping that conveys the water from the pump to the surface called drop pipe. And I'm going to show you some other schematics of those. And so in the day that we were there, this was all pulled out, and there was the video log of the inside of this well conducted. I'm going to show you some of that, and that's pretty exciting because it's sort of rare to get to see that kind of video. Well, with anything, there's a very broad audience, and so the understanding of how hydrogeology works is probably quite varied. So I'm just going to show you a few basic concepts so that if you lack awareness of it, you will get the gist of what I'm talking about. So we often show in many engineerings, but especially in geology, what we call a cross-sectional view of some system. And so this is as if we had dug a deep trench in the earth that intercepted this well, and we looked at it from the side. This would be the cutaway of the well. We saw pictures of the top of the well just previous to this. The water part here, this would be the aquifer that's being pumped or developed. pumps most of the time are hung inside the well. They're submersible pumps and they push the water to the surface. There are exceptions to that. And then many wells are equipped with a screen to keep the sediments out. We'll talk a little bit about that. And typically when before a pump is turned on, the water level here would be flat and it would span that level in the well. And when this pump is turned on, the water level drops, and we call that drawdown. It's drawing the water level down in the well. And the longer we pump, and the faster we pump, the further that level is drawn down. And we're going to see some results of that from some of the well records I'm going to show you of wells here in the Keweenaw. There's sort of two general types of characteristic types of water wells. The schematic on the left is showing a well that is installed in an unconsolidated formations. Those would be like sands and gravel aquifers. And with that kind of well, we'd have to have a screen placed at depth to prevent the sediments from flowing into and plugging up the well completely. And then I've repeated, or in the schematic is repeated, that drawdown picture of the water level. So the water level starts out up here, it gets pumped down, and then it'll often stabilize when the inflow rate to the well is matching the outflow rate of the pump. A little less common, but very common here in the Keweenaw and in the Western UP are what are called bedrock wells. And so bedrock well is, as we could imagine, installed in the bedrock, and they are installed in a different way. They're drilled just like this kind of well over here, but the casing is glued into or cemented into the bedrock, and then most of the rock up here is competent enough that if the drill continues down and is pulled out, it leaves an open hole. And so that rock surface serves as the well screen, so to speak. And then a pump is installed inside the borehole, just like a pump is installed inside a screened well. And the productivity of the water, or productivity of the well, depends on the number of fractures and cavities and porosity that this well intercepts. We'd prefer to have a well above the bedrock, but up here, when this unconsolidated, another term is overburden, is too thin, or the water table is too thin above that bedrock, we have to go deeper and install the well in the bedrock itself. And so this is sort of this needle in a haystack conception that I'm using, is that getting a productive well in bedrock requires it to intercept something very small that we don't understand very well, or putting a well in unconsolidated materials that are very rare here in this Keweenaw region, where bedrock is near the surface in most places. I'm going to show you a lot of well records today, or a handful of them. And well records help us and well drillers figure out where to drill, how to configure a well. It shows us information such as where the well is, when it was drilled, who owned it, the geology that it was encountered during drilling, the static water level, that's the water level prior to pumping. And then often there's a pumping test, short pumping test performed, and we can see how far the water level is drawn down at the pumping rate. We can also see other design configurations. This particular well has a screen. We can see it's 8-inch diameter well, and it's actually the well log for that hatchery well that I showed you in an earlier slide. And there's other information like who the driller is, if there's potential contamination nearby, and other useful information about the well. We can access this in Michigan from a utility called GeoWebface, and they're all publicly accessible. And you can, any one of you can look this up, and I have links in the last slide of this presentation on how to find these. But we turn on the layer that shows us the wells, and we select a well. And when we select it, we get this information, brief information, and then there's a hyperlink here we can click and get a well log like the one that I just showed you. We can download it. And that's what I did in preparation for this talk. So I've worked with a number of wells up here over the 30 years I've been a professor at Michigan Tech. And so I picked out some select ones that I thought would be of interest, primarily community wells. I thought I'd start out with is showing you the inside of a well. And this one is not in the Keweenaw. I don't have a video log of a bedrock well. This is a bedrock well. This picture here is of a downhole video camera. And so it gets lowered down the well and it can take a video image looking down. And that's what you see here in this thumbnail for the video. And then it can be turned to show video sideways to look at the side of the borehole. So for this particular well, it's at the Thompson State Fish Hatchery, which is near Thompson, Michigan, the south central part of the Upper Peninsula. And I'm going to show you some video of this section here that I highlighted, about 170 to 180 feet down. The driller noted that there was a void here, and I'm going to show you that. I'd also want to mention that this is actually an artesian well. When it was drilled, water rose above the ground surface, and it could flow at about 100 gallons per minute without even having a pump in it. So let's look at the video. So when you see it go sideways, you're looking at the side of the borehole. So this is an example of a fracture. So that if you didn't read the lithology, this is a limestone bedrock. So most of the bedrock is relatively low permeability. The number that you see in the center is the depth from the ground surface. And so you're going down the hole here, and then you'll see the video camera turn sideways. And so now we are in that part that was noted as the cavity. So during the drilling process, I imagine part of this cavity existed and then it was created larger as a result of the drilling process, and they had to clean that out. So the hole diameter was about 10 inches, and this cavity looks to be another, rough 2 or 3 feet out into the formation. Okay.
All right, that's just really cool, John, I'm saying. I've never been down a well before.
Yeah, I think it was really awesome to see. I was really grateful to get it from Eric Kleiman. Right. Oh, I need to get back to my sharing here. There. So now I'm going to show you a well that's in unconsolidated materials. And so in an unconsolidated formation, we have to use a well screen to keep the materials from falling into the well and plugging it. And the most hydraulically efficient well screen is what's called a wire wrap screen. So I just have a schematic of one here, a picture of one being fabricated. So there's these longitudinal rods, and this wire is wrapped around and welded wherever it touches the rod. And the spacing between the wire is adjusted to keep out various sediment sizes. I noticed a few students in the participant list today that learned how to do this in classes from me, and hopefully they still remember. And then this image at the right is the cover of a book that I used for the class. So you see this wire wrap screen and how it's preventing these sediments from coming into the well. So this is my other video I'm going to show you. This is the inside of Hatchery Well 3, which has a wire wrap screen. So when you're seeing it from the side, you're seeing those wires and those that are wrapped around those longitudinal rods. And then this well log over here is well 4. So it's a little complicated. I don't have a video log of well 4, and I don't have a well log for well 3, but they're very similar. So I'm using this well log of 4 to show you approximately where we are in well 3. So we're down here in this bottom where there's sand and gravels outside the well screen, and the well screen is completed in those coarser materials. So we're starting at the bottom of the well. This is again well 3. So it is at 277 feet deep. We're at the bottom now looking down. This is an 8-inch diameter well. And then you're going to see it turn sideways now. Now we're looking at the inside of the screen, trying to look out. And if you squint, you might see some geology at some parts. And then other places, the geologists that are online are noticing what looks to be like gravel sticking out. Those are precipitates. Minerals are precipitating in the well screen and the formation around it. And this is what we envision is causing the reduction in performance of that well, is that precipitation. And we worked on some things related to cleaning that up.
Well, and they're nucleating on the screen just because it's there.
Right, and that's where the water pressure is the lowest, so where the precipitation is most likely to happen. There's probably a lot more precipitation that's occurring out in the formation on the outside of the screen.
Mm.
All right, well, I'm not gonna,
Fascinating.
yeah, it is. I'm happy to talk or answer questions about that at the end. But today I'm just gonna focus on water productivity of wells.
Do they always record them as they're going down with the cameras?
No, this was because we were trying to figure out why it was plugging.
Okay.
It's actually very rare to get a video log. That's why I wanted to share it tonight with everyone. So we're going to look at some more well records, and I have 2 screen captures of the Geo web face map. And in the background is the bedrock geology of the Keweenaw. And I have that as my background here so that to help remind you of the rock types as we go through this sort of travel log of water wells in the copper country. The red locations are community wells, and the green ones are residential wells or private homeowners. The rock types here that we're going to look at, this pink is a Jacobsville sandstone. The brown is the exposed edges of the Portage Lake volcanics. This tan is the Copper Harbor conglomerate. There's a thin exposure here of or exposure expression, I should say, of the Nonsuch Shale. And then this light blue over here is the Freda sandstone. We're not going to talk about that. We're just mostly going to focus here in the Keweenaw. So the residential wells, these green locations, are dictated primarily about where homes are. And you can see they're heavily concentrated along shorelines. And if I had roads on here, there'd be a lot of roads that they're concentrated on. The community wells, on the other hand, are selected more based on the geology to get productive or high productive rates. So here's a table that I put together from some information from a couple of sources on some of the community wells. And so they're going from the northernmost part of the Keweenaw down to the south. Most of the time, communities get their water from groundwater from a well field, so more than one well. And that's in part because sometimes more than one well is needed to draw sufficient water for the community. And then there's some redundancy that we want to have in case a pump breaks or some collapse happens, or we need to have a lot of extra water to fight fires or some other purpose. So I have listed or highlighted over here some of the wells that have very high productivity. So on the order of hundreds to a few thousand gallons per minute. And then there are some here highlighted in the north that are more on the 20 to 100 gallons per minute. And one down here highlighted down in the community that I live, but I have my own well down there, and very low flow rate are capable of these wells. And these are in the, as you will see, in the Jacobsville sandstone. This column here is the number of wells that are in the well field. So if we just compare Houghton, right, which is 10 times or more, 20 times sometimes bigger than Chasel, depending on the time of year, it only has half the number of wells. And that's because it has wells in a very productive zone. We're going to look at some of these, not all of them, but some of these in relation to the geology. But we're going to start with the hatchery because I've worked there now with students for 30 years, and that's probably where I've done the most water well work. So we're all familiar with where Baraga and Lawrence is, and for those that have traveled in an adventuresome way up north of Lawrence, there's a land feature here called Paquaming Point, and it's very unusual. And the hatchery is located right here. So in this diagram, right about here on this feature. And I have here a line drawn through cross-sectional line here to show the elevation profile because that has something to do with the story. So over here on this part, this is Pequaming Point. Oh, sorry. This is the upland part up here. And then this flat part is this region out here, and the hatchery is right here on that, where that starts. So one might ask, do we always have to drill a well to know what the geology is? And that's sort of like, do we have to cut a tree down to be able to tell how old it is? Well, in our department, some of our majors are applied geophysics majors, and then our geology and geological engineering majors learn about techniques called geophysics, where they measure things about the subsurface without having to drill a well. And so one of the techniques that are used in groundwater exploration is called gravimetry. And this is a gravimeter here, a picture, a stock picture that I took. It collects data that looks like this, and it can be interpreted as a cross-section where this might be the bedrock profile, and this would be the profile of the unconsolidated materials above it. And so we might naturally look for a place that's deep, where bedrock is deep, to put a water well. These can also be conducted in an aerial way and then mapped to look at anomalies. And in this map, these anomalies here are where bedrock would be deep. We happen to do this with students from our department. They ran a gravity survey along the roads here. And here. And then based on that, they created a map of the depth of the bedrock. So the redder these colors are, the deeper the bedrock. The deepest part is over 300 feet deep. And then the cooler colors are where bedrock is shallower. And so up here, the bedrock is 40 feet deep or so. Here it outcrops, but there's a trough of that bedrock valley that's been filled in with sediments over geologic time. So this is the data the students had, or the data the students collected was interpreted for one of the profiles, gravity profiles along that road. The hatchery would be over here, and Pequaming Point would be over here. This is thought to be a cross-section of a glacial tunnel valley. So when the glaciers were melting and they were stalled, that meltwater was flowing out underneath the glacier and scouring that erodible sandstone and creating a ditch. And then later with time, those ditches filled in with sediments and formed the basis of these aquifers that the hatchery and some of the residential homes nearby are tapping for their groundwater source. Schematically, this is what it would look like. It turns out those hatchery wells are very deep, 270 feet deep or so. And they're below a sort of a clay aquitar that somewhat protects this deeper aquifer and also pressurizes it and makes it a little easier to get water out of it. So again, just as a reminder, these are the hatchery wells, these three right here, residential wells elsewhere. And this is the bedrock. So those hatchery wells were, the hatchery was sited purposely to be in this bedrock trough. So Lake Linden is also a really interesting situation. The wells, these are the community wells here. And those wells are almost 300 feet deep and they don't hit bedrock. But this well right here, bedrock is at about 20 or 40 feet deep. And I believe this is also in a glacial valley. And you can sort of see it. So here are those wells that are in the community wells in Lake Linden. If you squint, this to me looks like the surface expression of an underlying valley that has been filled in. That well where the bedrock is shallow is right here where the sandstone changes to those Portage Lake volcanics, and those volcanics were less erodible, so they're closer to the surface. The Holden well field is south of campus. The Christ gas station just south of campus would be right about here, and there's this nice homes out on this point or peninsula. These wells are very shallow, only 50 to 60 feet deep. The materials they tap are very coarse gravels and cobbles. And these are highly productive wells. One well can produce about 1,500 gallons per minute. One well is probably sufficient for the community during the summer. 2 wells are sort of needed during the school year, and then 3 wells probably during winter carnival. These wells have a screen that are in that bottom 20 feet. There's 3 wells there. The Holden wells are surrounded by wells that are in bedrock. So the closest one is here. And this is in the Geological sandstone. And the homeowner here has a well that's about 300 feet deep, 200 and some feet of it in the Geological sandstone. And they can only produce, maybe 50 gallons per minute. But here, these are producing over 1,000 gallons per minute, and they only had to go 60 feet deep. I didn't go and look at all of them, but these are also shallow wells, but in bedrock. Dollar Bay gets their water from a formation that's just like this. In fact, geologists I know sort of think that this is probably the same formation that goes underneath the portage of these old glacially deposited gravels and cobbles. I mentioned I live south of Chassel. Chassel has 6 or 7 wells. They're all clustered here. They don't have a bedrock valley there, or none have been found. So here their wells are a couple hundred feet deep, and they're all in the Geological sandstone. And at best, they can produce about 20 or 30 gallons per minute, which is inadequate. One well would be inadequate for the community. It's plenty for a homeowner, but too little for the community. So they have to sort of accumulate water by using more than one well. I know there's some people that are interested in the water supply for Hancock. Hancock's water comes from some mines actually in south of Painesdale. Here's a picture showing the facility here in these wells. This is their location on a map. And here's the well record for one of those wells. So this is not a bedrock valley well. It's going through alluvial deposits or glacial deposits to 80 feet or 100 and some feet. And then they punch through some hard rock formation, and they case, that well is cased all the way to that bottom part. It's a 22-inch diameter hole, 14-inch casing cemented in. And the water level they hit was 187 feet deep. And then they pump it for 3 hours at 1,200 gallons per minute and stays at 187. So essentially what they did is drilled down to intercept the mine shaft, and the mine shaft acts like a well screen or a borehole. And because it's so big and connected, then it can produce a lot of water. All right, I'm gonna turn it over to questions here, but first of all, I just wanna acknowledge some dear departed friends that has coached me a lot about water well drilling in the Keweenaw. They're pictured here. The 3 legends of water well drilling all passed away within a few years of each other. Harry Kleiman down in Iron Mountain. His company is the one that provided those video logs. Dave Sertla drilled the well, or his crew drilled the well at my farm, my irrigation well. And then Larson Well Drilling did a lot of the wells out at the Keweenaw Bay Indian community. And I want to thank those that I've worked with at the Keweenaw Bay Indian community and involving my students in those projects. I also really appreciate these companies and the advice and explanations, practical explanations they provided my students on water wells here in the Keweenaw. I mentioned that there are some references, so the GeoWebface link is here. In the past, when I've done a Husky Bites, we've posted the slides so you'd be able to access these and get the link. So I have some links available for you if you want to pursue any of this on your own. I think that's it. Yep.
Oh, that was really fun.
Yeah, that was really interesting, John, and you've generated quite a bit of interest online. If you're ready to try to field some questions.
I'd be happy to.
Okay. Well, I'll try to, some of these are related to each other, and I'll try to do some consolidation here. But one of our online listeners is interested in the types of pumps used in the wells that you've shown that are able to generate these many hundreds of feet of head. Could you
Yeah.
tell us a bit about that?
Yeah, so they're centrifugal, they operate on centrifugal motion. And so they're submersible pumps. And these submersible pumps have the motor on the bottom. And so that the first one I showed you, sorry. Let me just get out of that. To that picture. So this is the pump part right here. And the motor is down here. And the intake is right here. And so the motor spins the pump pushes the water up and sucks in water through the intake. Now, some people have seen pumps, you've probably seen these in agricultural settings where it looks like a mechanical mushroom on the top of the wellhead. And those are agricultural wells. That's called a vertical turbine pump. This submersible part is still the same, but the motor's on the top and there's a shaft that goes down to turn the pump. Those are the most common for pumping water at high rates. If you don't need a high rate, but you want to do it in a reliable and in a way that's economical and against a lot of pressure, then you use a positive displacement pump. So like a piston pump. And that's the principle that the hand pumps work on, is that.
Okay.
The most common.
Yeah, it's very interesting.
But there's
Now,
a variety of other types too.
Okay. Now, this well that we were looking here, there's some issues with clogging with that well screen, right?
Yeah.
Well, so some folks were interested if there's anything you could do to redevelop that well, or things that you could do to clean it from the inside, or is that going to cause more problems? And then on a related note, does the well screen material affect this precipitation?
Yeah. So okay, so I'm going to do that last question first. So that's stainless steel screen. So not much sticks or erodes that, sticks to or erodes it. There are techniques to clean a well. So the first method that was tried was a scrub brush. So you have these special scrub brushes that get pushed down the well, and it's just like plunging a toilet. You just go up and down until things get loose. In this case, the plugging was inside the well, and in the well screen didn't look to be a lot. And so after that scrubbing and retesting the well, the improvement was about, we doubled the rate, but not as high as what it used to be. So then we wanted to do what's called an acid treatment. So old timers here might remember about using tablets to clean dentures. Well, dentures have plaque on them. Well, essentially this is a mineral plaque on the outside of the well. So if you put an acid in the well, a strong acid, let it sit there, it'll permeate out into the formation, dissolve those minerals, and do that for about a day and a half. Then you pump it all back out. So it's a pretty common technique, and we wanted to try it here. The problem here was that we were concerned about capturing some of that acid in an operating well and then killing the fish. So the student project actually was involving determining whether these wells were hydraulically connected, and if during the acid treatment, if we would suck up some of that acid water in a producing well and kill the fish. So we did a salt tracer test that was harmless for the fish to sort of show that that wouldn't happen. And so we did an acid treatment, and we tripled the productivity of the well. So we went from doubling it to tripling it with that acid treatment, and made it, which is better, but we probably should have been doing this maintenance earlier and just hadn't been monitoring it. We didn't have the ability to monitor it until a few years ago.
Okay.
Well, I think I see a question directed to you, Eric, about how dissolved oxygen is added to the well water. And you might want to explain why we would want to do that as well.
Yeah, well, the oxygen levels I don't know how those vary in these wells. Some of them, and John maybe knows more about the water chemistry in these wells. Some of them might have fairly significant oxygen levels, depending on what kind of reactions are occurring in the subsurface and where the source of the water is. Do you have any information on the water chemistry in terms of like dissolved oxygen in these wells? And do they have to do anything to enhance that in these communities, John?
Yeah, well, thanks for asking me a hard question that's more in your expertise.
Well, I thought that's a classic professor thing. Well, I don't have any.
I can answer.
You know, certainly.
So I do know that there's oxygen levels, as you know, and you've told me before, are naturally low in groundwater. And in fact, that water that gets pumped out of the ground goes through an air stripping tower before it goes into the tank with the fish, in part to introduce oxygen into that water that's going to go into those tanks.
Okay.
The minerals, the naturally occurring minerals are manganese and calcite or calcium. And then when you pump and reduce the pressures, those minerals come out of solution, precipitate, plug the formation. That causes the pressures to reduce further. So it's a cascading effect then.
Right.
And that's happening out probably in the formation right next to the screen where the pressure reduction is the greatest.
Mm-hmm. Interesting. Yeah, you're right. With the oxygen levels, some of these aquifers are pretty low, and that's an issue we run into with cleanup or remediation of these aquifers if they're contaminated by petroleum hydrocarbons or something like that, where we might use microorganisms to break down the hydrocarbons. And they're one of the things that we focus on, as you know, with your work with air stripping, and my work is trying to get enough oxygen into the well to stimulate those processes. So that's definitely an issue in that aspect of it as well. Now, for some of these communities, there's some interest. Folks are asking online: what are kind of storage facilities do these communities have? Do they have water towers or larger tanks that are associated, so they can store water in when the demand is low and they're pumping?
Yeah. So there are elevated tanks. So like the Holden tank, the Holden storage tank, and then Holden also has storage tanks they're elevated up on the hill. They're up on the hill, so they're elevated for most of the community, but they're not on a stand. And so that's all part of the water distribution system. So I don't know how the pumped water gets connected, where it gets connected to that, but that water is going up to the tanks and it's also going out to the grid.
Right.
And another, in Pequaming, so one of the defining characteristics of Pequaming, when you drive through Baraga on a sunny day, you can see their water tower shining up in the sky. And so so there's obviously a pump there for Pequaming, and it's pumping up to the tank.
Right.
Tanks are used for the,
Oh, sorry to interrupt you, John. Go ahead.
Oh, that's all right.
Well, and of course, the struggle that the communities have is that their demand is varying throughout the day, right? But they're pumping at probably a fairly consistent rate. And so storing when demand is low and then drawing down their storage when it's high. I guess that's something that might vary between a community and the hatchery, or is the hatchery's demand also fluctuate with time?
The hatchery demand fluctuates. They don't have a storage tank. It fluctuates based on how many fish fingerlings they're rearing at a time. But that flow through those tanks is constant. So they're pumping continuously every day, all day. Just the rate at which they pump varies depending on how much water they need. And so that water goes up in, like I said, over an air stripping tower. It's not stripping, it's using that to infuse or dissolve oxygen in the water. It is stripping out some naturally occurring radon. And then it flows by gravity through the tanks and then discharges to a wetland, carrying the waste from the fish with it. And then that eventually goes to the lake.
Okay. Now, we were talking about Houghton's system there. There's some questions about Houghton, why it was located there in that so-called sands area. I think you probably answered that's probably largely due to the geology, but then another person was wondering they had heard when they were here a student in the 70s that Holden got its water by tapping also the Isle Royal mine, similar to Hancock's approach. Is that true to you or not? You know,
That part I don't know. I know the Holden Wells were drilled in the late 70s.
Okay.
Well, and we have an interesting comment from quite a few comments from Bob. Hi, Bob. Bob Carnahan's one of our super alum. So he said an early project of his Universal Oils lab was proving viability of nickel-free stainless steel during a chromium scarcity in manufacture of Johnson screens. Nickel is, yeah, because stainless steel usually contains iron, nickel, and chromium. So yeah, that's interesting. You were working in the support of Johnson screens, Bob.
Yeah, they're a well-known manufacturer. And I saw that Bob had another
so many questions. I'm sure you can see some of them too, John.
Yeah, I'm trying to answer a few of them, but there is I did want to turn a question over to my colleague Eric, because there's a lot of questions about why is groundwater being used, let's say for Chassel instead of using lake water. So in that one table I showed, Barriga and Lawrence get their water from intakes, but other ones like even Calumet, you know, they get water from wells on the shore of the Keweenaw, but not from the lake. So do you want to comment, Eric, on why communities are choosing groundwater wells instead of building a water treatment plant for surface water?
Well, I can try. I see I'm getting a little bit of my own medicine here from earlier, but well, you know, I'd say historically we consider groundwater to be kind of protected, right? And as opposed to surface waters, which are easily contaminated by, you know, the surrounding land and runoff and other human activities, agriculture and mining and things like that. And so with groundwater, with all its depth and protection by the overlying sediments, you know, our sense was that it was protected. And to a large extent it is, but, you know, as we found in a lot due to past inappropriate disposal practices of wastes and perhaps septic tank systems that are not maintained properly, that, you know, groundwater does get contaminated and require cleanup, that, you know, the topic that you and I have both worked on. So I would say that's probably one driver, that it's considered to be clean. Although, you know, interestingly in Marquette, you know, they're taking their water from Lake Superior, which is quite a clean, you know, source of water. And so they have a fairly unique treatment system there for their drinking water. They don't use the kind of chemical precipitation and coagulation systems that a lot of surface water systems have to use to settle out all those particles and the microorganisms that they might harbor that could cause disease. Instead, they have because it's so clean, they can just, you know, filter it and then disinfect it before distributing it. So, you know, it really depends on you know, Lake Superior is quite a clean surface water source historically. But I would say, and maybe, you know, you might want to, you know, add more to it, that a lot of it has to do with the sense that groundwater is protected and a cleaner source of water, and a more reliable source, perhaps.
Yeah, so someone else asked, this is a common question when I talk about hatchery wells, is why, if they're so close to the lake, they just don't grab lake water, you know, and a hatchery operation is biosecure. So they would have to disinfect that water to in a very expensive way, in a very thorough and reliable way, and test it to be able to use that for the fish. And so by using groundwater, you know, that groundwater is not contaminated with diseases that the fish might inherit. And so that's why they're using groundwater instead of a surface water source. And which is your answer about why we don't necessarily, the treatment of surface water, the expense of that is high enough that groundwater as an alternate is often advantageous or cheaper, more economical.
Right. And of course, at individual wells, they're often using that water with minimal.
Yeah.
Well, and Greg has a well in the Keweenaw Peninsula on Little Traverse Bay. We tend to have what seems like dissolved gases in the water. The hot water tends to accumulate more gas in the water lines. gases are expelled when water is used. Any guidance on what's causing this?
Well, yeah, so naturally there's gases dissolved in water. So carbonic or carbon dioxide dissolves in water and forms the carbonic acid, right? And it's that gas that comes up, probably predominantly comes out of solution. And when pressures are reduced and things are heated up. I don't know why that particular situation has more gas in the hot water. It could also be, I don't know this for sure, but just guessing, is that the water level might get pumped down enough that there's some air getting drawn in from the pump and causing some chugging. And so that's possible. Unfortunately, with water well problems, because they're hard, everything's below ground and you can't just pull it out and look at it. It's like a mysterious car problem, electrical problem on cars, you know, where you can't, they're really hard to diagnose, and there's usually more than one possibility.
It's like car talk.
Yeah.
Well, and Mark asked, are there artesian formations in the UP that you come across?
Yeah. Actually the wells at the hatchery are the first one was artesian, but then during pump, you know, as a result of pumping that, it reduces the artesian conditions. There are a number of wells out. There's artesian wells. A lot of locals know about them. They tend to think there's some sort of health benefit to them or spiritual benefit, and they go and collect water in jugs from those artesian wells. I know there's one down on M38. There's one up in the Keweenaw that I know of.
How do we know we have an artesian well?
You have to punch through the geology and put a pipe in there, and then if the water comes up above the ground surface, then it's a flowing artesian well. They tend to be located in similar regions on a very small scale or very narrow scale. So that artesian well I showed you from the Thompson State Fish Hatchery, that is very near the big spring, Kitch-to-Kippy, which is essentially an artesian well, but a natural one in the rock. And so I suspect that the hatchery is tapping water from an adjacent or the same formation, and it's pressurized. So recharge areas, if they're up in higher elevations, they pressurize the water, and you put a well in lower elevation, then you have the chance of it being in our flowing artesian well. Unfortunately, there's no way to measure that with geophysics. If there was, that geophysicist would make a lot more money in water well exploration.
There's so many questions. I'm just going to keep asking them kind of a little bit randomly. Yeah. Brendan wants to know how deep are residential wells on the shoreline? And let's call this on the Houghton shoreline.
Yeah, so if they're in the bedrock, the wells often have to have at least 100, 200 foot of water column. So if the inflow to the well is really low, like it can't sustain the pumping rate that's needed, they drill to hold the well deeper, and the well itself is like a storage tank. And so it pumps out, you know, during the day when people are using the water, and then it shuts off. And so the water that's coming out of the well is coming from the volume in the hole. And then overnight it recharges itself, you know, fills back up. So a lot of those wells are that deep because of that. They're low productivity and they need to have that storage capacity. On the west side of the Keweenaw, on the Frida sandstone, though that aquifer, the water levels in that aquifer are much deeper, and so that you have to tap more deeply. And then one of Gina asked the question, well, why are some of those salty? And there are wells over there that tap what are thought to be ancient brines that have been trapped for geologic time. And when some of those wells get too deep and they start intercepting some of those salty waters, it makes the water unsuitable to drink. And,
that's interesting. Ancient, I would drink some ancient salt water.
Well, not for long, but we tried to use electrical methods in geophysics to see if we could measure or detect those, but it was so deep that, and most of it is probably, you know, in that near shore region that we couldn't get deep enough with our instruments to detect it.
I think we lost Eric.
Yeah, it seems like it.
I thought he would.
Yeah, I think he can only stomach me for about an hour. So
We're going to just take a few more questions. And then I know, and then we're going to wrap it up in about 5 minutes.
sure.
So there's a couple questions about contamination I don't think we've answered. So the first one's from Tom. Have the stamp sands in the area contaminated any of the groundwater?
Yeah, so not that I know of. The stamp sands have been deposited mostly on the shore, and then the areas where it was deposited up in the Keweenaw and watersheds, I know the surface waters have been impacted, but I don't know if any deeper groundwaters have been. In the Holden case, so Tom might remember that those Holden Wells that whole landscape used to be devoid of vegetation. It was all stamp sands. And those wells punched through those stamp sands. They also punched through a clay layer, pretty compacted clay layer beneath the stamp sands, tens of feet beneath the stamp sands. And I believe that clay layer serves as a protecting layer from infiltration from above. It also pressurizes that water so that most of the water that goes to the Holden Wells comes from upland. That the computer modeling that we've done shows that it comes sort of uphill. That's typically what happens, seeping from that sandstone into that gravel cobbly aquifer. So the waters that are pumped out of the wells in Holden don't seem to come from the portage. Those wells seem to be intercepting water that would be naturally discharging to the portage.
All right, so we have no fear around here from stamp sand poisoning. And then it's nice to see Nicole out there. Hi, Nicole. Nicole is one of our Alaskan, well, not Alaskan, she lives in Alaska. What metal concerns have come up, I guess, with wells in the area? Are there any metals that are considered background? And that'll be the last question, and then we're going to wrap it up.
Yeah, so uranium is a heavy metal. It occurs naturally, and it turns out it's present in detectable levels in the Jacobsville sandstone. In fact, in the 70s, there was a government-sponsored exploration activity here in the Upper Peninsula because it was thought that there might be mineable quantities of uranium, and that was during the Cold War. And of course, there was a lot of interest in uranium for weapons development. And so one of the things they did is they went around, drilled wells and measured the water, uranium in water. And they never found quantities high enough to sort of indicate an ore deposit, a uranium ore deposit. However, at the time they didn't think about it, but the quantities that were dissolved in the water were high enough to make the water hazardous. And so there are places here in the Keweenaw and other places in the Upper Peninsula, wells in Jacobsville sandstone, where the uranium levels are high enough that they're above the maximum contaminant level promulgated by the EPA. And that the hazard they pose is not a radioactive hazard at those levels. Its behavior as a heavy metal. And
interesting.
And one of my students, PhD students, Heidi Sherman, did her dissertation work on that. And so the library here at Michigan Tech has her dissertation online that people can access, and people do access it. That shows maps of where she had sampled wells and did some geophysics to measure uranium in boreholes. And so I would look up in the Van Pelt library, Heidi Sherman, uranium and sandstone. And we also have a paper published in Groundwater Monitoring and Remediation on that work. Turns out, as Eric mentioned, I'm from the Sioux. And in my last Husky Bites talk, I mentioned how I currently live over the Jacobsville sandstone, and I previously lived over the Jacobsville sandstone in the Sioux. And I was home visiting my brother and sister-in-law when we were doing that work, and I was mentioning this to them about the uranium. And my sister-in-law insisted that I sample the water, and sure enough, next time I visited, I installed a reverse osmosis system to remove the uranium from their water.
Well,
oh my gosh.
I apologize for dropping off there. My teenagers came home and hit the internet and killed my connection. So I had
Well,
disappeared for a while, but
well, I'm glad you're back. And we determined last season and the season before and the season before that you can never hit the end of the Husky Bite questions. So we have 30 open questions. We've answered 21, but we're coming up on the hour. And I would like to ask each of you to just give some closing remarks. And before you do that, just to thank you both for your time this evening. And I learned a lot. And John is our first time back double speaker. So, I think that's a sign of, wisdom or something like that you've been asked back.
Or desperation. Got that before Seagren did.
So Eric, just some closing remarks from you, and then John, you can wind us up.
Well, I thought it was great to have the interaction with the audience and all the great questions. Dean Callahan, thanks a lot for helping to field those. There was so many to look at and think about. So many good probing questions by a lot of our alumni out there, and I think that's great, and enjoyed that. And it was fun to hear John's presentation. It was something I didn't know particularly about the community water wells in this area, so I enjoyed it a lot. So I appreciate the invitation to participate, and I really enjoyed myself. And good job, John.
Well, thanks. Yeah, so I thanks to you, Janet, for inviting me back. I'm not only the first return, I was the first one. I kicked it off this series in 2020. And so I appreciate you inviting me back. And I don't know if you remember when you asked me to talk then, you wanted me to talk about geology. And I said, I don't know much about geology. I know about wells. And she said, that's boring. Geology. And she goes, and I don't remember if she said, well, maybe I'll bring you back and you can talk about water wells. I mentioned my gratitude to those well drillers, and now I still work with their families, at least with Larson and Kleiman on continued water well projects. And I just want to say that I'm really grateful to have had that experience, to be able to incorporate that in classroom activities and classroom projects. And so some of the alumni, I didn't get to go through all the list. I just poked around now and again. I saw Ann on there. I know she took classes from me. Andrew was online, and Austin. And having that information to be able to present that in classes that I teach to increase the practical awareness of these things for students and give them things, that pictures and videos that they can see and feel a sense of place with, I think is really valuable. And it really helped to have well drillers that were willing to listen to a professor's questions and someone who doesn't really know like the practical side, or I didn't until I talked to them and only knew the book side of things. And so I really appreciate having that opportunity to learn from them so I could share it with the students.
Well, if people still have questions, are you willing to share your email, John?
Yeah, I mean, people reach out to me a lot. Yep. Do you want me to put that in the chat?
Or just say it out loud, maybe?
Oh, J.S. Gierke. So J is in John, S is in Scott, Gierke, Gierke at mtu.edu.
Awesome.
One of the other I've done is design solar powered pumping systems. I have that at my irrigation well at my farm and for others. So I can give you advice if you're doing something like that.
All right, well, let's wrap it up. See you next week, folks, for Husky Bites. Thank you again, John and Eric. It's been a pleasure to spend the evening with you. Thank you.
All right.
Thank you.
Thanks again.
Goodbye.